Okay, so we're continuing with solving equations. And in the last video I introduced the three-step process. Right? This is a general process that works for every equation you're ever going to solve. You don't need to remember different rules for different operations, different levels of complexity. No. To solve an equation, do you remember what they are? Step one, simplify. Simplify each expression independently. Once each side is as simplified as possible, then we can introduce the same new operation to both expressions. Right? Now we need to be wise in what new operation we introduce. Just adding 100 to both expressions probably isn't going to be very useful. So let's get to the third step, which is to just repeat. Now there will be situations where we actually want to start with step two. There will be times when we don't want to simplify completely based on the operations and the numbers that are in that particular equation. But let's get to a few examples of the simpler variety. Right? Let's say I have x plus 7 or x times 7 . I can't simplify this. I can't simplify this. There's nothing to do in step one. I can't simplify this. I can't simplify this. There's nothing to do in step one. Right? I can't do the multiplication without knowing the value of x. What I can do is introduce this new operation here of plus -7. Now, one nice thing about always using plus instead of sometimes subtraction is I didn't really have space, I thought, between the 7 and the equal sign. So instead I could put it out in front. Right? If I had written -7, this doesn't mean -7. This all of a sudden turns the x into a negative x. 7 minus x is not the same as x minus 7, right? We have to be careful about how we're doing that. But if I write it as a plus with a 7 is negative, I can put it out front or behind either way. Same thing here. To cancel this times 7, I can multiply by its inverse. Do the same thing to both sides, right? Associate 7 plus -7 is 0. Let me change colors again here. 7 plus -7 is 0, and 0 plus x is just x. 10 plus -7 is 3. So if 0 plus x is 3, x is equal to 3. So the solution is 3. Now, if I had my druthers, I would have you write this every time. Right? The directions that I didn't even put up here, right? What I'm asking you to do is to solve. So my answer is the solution is 3. But most other situations aren't asking you to type in this whole sentence. For one thing, the AI automated systems can't really understand the syntax of this. They just want to recognize the number input. So they're just going to ask for the 3. Some people recognize that this is kind of synonymous with saying the value of x that works is 3. So some people are happy with that. On the computer systems, usually just a plain 3 is what they're looking for, right? And they've already written the solution is, or x equals blank, right? But these are all really saying the same thing here. Over here, I can use the associative property of multiplication. 1/7 times 7 is 1. And 1 times x, that's the multiplicative identity. 1 times x is x. I've now simplified this. Over here, 10 times 1/7, no common factors, so I just have 10 divided by 7. right? No need to mess around and be fancy and say, well, that's 1 3/7. Don't waste your time showing off. Improper fractions are just fine here. Now, what if instead of addition we start with subtraction? Say x minus 7 is 10, or x divided by 7 equals 10. Well, the same thing. What's the opposite operation of subtraction? Addition. So I'm going to bring in here a plus 7 and a plus 7. 7 minus 7 is 0, or I could just change this on my paper. Minus 7 means plus negative 7. Associate these two, I get 0. 10 plus 7 is 17. There we go. Now I have the simplest equation of all. The solution is 17. The value of x that makes this true is 17. So the value of x that makes this true is 17. So the value of x that makes this true is 17. And I can check that. 17 minus 7 is 10. 10 is equal to 10. I can check this. 3 plus 7 is 10. 10 is equal to 10. All right. Over here, I really prefer the fraction version, because here we can see that associative property at work better. You could say divided by 7 is x times 1/7. I think that's a harder sell. But for all of these, I'm recognizing to undo that dividing by 7, I multiply by the reciprocal of 7. 7/7 is 1. 7/7 is 1. Here, to say x divided by 7 times 7, it's a little harder to see that that's not x divided by 49. Right? We're kind of used to visually seeing the multiplication together with something else separating it. But dividing by 7 means dividing by 7. Then multiplying by 7 doesn't go with the 7, it goes to the whole expression here. Right? So I'm multiplying this by 7. 7's cancel, I get 1. If I introduce a times 7 to the left expression, I have to introduce a times 7 to the right expression. If I'm balanced here, and this side suddenly becomes 7 times heavier, I've cloned the child on this side of the teeter-totter. Now I have 7 little Billies. Well, I also have to clone Sally on this side, get 7 of those, so that it stays exactly balanced, right? So if this side is 7 times heavier, now it's a single x. This side has to get 7 times heavier. 10 times 7 is 70. 1 times x is x. So x is equal to 70. So I would say the solution is 70 over here. 70 divided by 7 is equal to 10. That's true. The solution over here is 17. 17 minus 7 is equal to 10. That's true. So for any operation, I'm introducing the inverse for that operation in order to cancel it and get x by itself, so that I have a super easy equation that the solution's already staring at me. So let's get back to our original fancy one here. And let's see if we can apply our principles to this equation. So first step, simplify each expression independently. So I have a 13x plus 7x, that's 10x, plus 15. And then these have a common factor of 5, which is going to cancel, so it's helpful to factor that out. Right, 5 cancels with 5. Now I have my variable being multiplied by something. Can't simplify that. Then plus 3. Can't simplify that. This is as simplified as I can get. Now I'm over looking at this side. 8 is moving forward, the 3x is moving backwards, the 2x is moving forward, but they're both x's here. I can say negative 3 plus 2, both talking about x. Negative 3 plus 2 is negative 1. So I'll just say 8 minus x. And that's as simplified as I can get here. This is often where we're going to get started, right? We have this kind of general form where we have x being multiplied by something and then a whole number being added to that. Maybe not a whole number, just some real number. And then over here, the same thing, right? Whereas 8 plus negative 1 times x, however I write that. When we're in this situation, our goal is to get to this situation, right? Where my variable, usually x, but it could be anything, where my variable is written just once, no other operations happening to it, and it is balanced with some number. So how do I get from here to here? Well, I have 4 choices. I can add the inverse of this. I could add the inverse of this. I could add the inverse of this, or I could add the inverse of this. If we look back at these examples, what's going on here? If we look back at these examples, this minus 7 kind of got moved over here to a positive sign. I added the inverse of the 7. That left me with just the x without this term. And now I have 2 terms over here that were like terms, and I could combine them. Right? Whenever we have multiple terms, our goal is going to be to get rid of the one that's unlike and move it to the side where it has a like term to combine it with. So over here, I have the 2x term and the 3 term unlike terms. The 3 and the 8 are like terms. I want them to be in the same expression. The 2x and the negative x are like terms. I want them to be in the same expression. So my personal preference, and you have complete freedom in this, but I don't want to waste your time solving it 17 different ways. So my personal preference is to move the x's first, usually. So I start at 8, I move to the left x. If I move to the right by x as well, here's my number line, here's 8, I moved to the left, now I'm going to move back to the right by the same amount, I'm right back to 8. Right? Negative x plus x is 0, just like 7 plus negative 7 is 0. Right? So that's going to cancel. Writing 8 plus 0 is kind of tedious. We recognize, okay, I'm getting 8. If I add x to the right-hand side, I have to add x to the left-hand side. There's plenty of space here, so I'll just put it at the end. So now I have 2x plus x, that's 3x, plus 3. 3x plus 3, 2 terms, not much different than 2x plus 3. But now on the right-hand side, 8 as a single term instead of 8 minus x as 2 terms. I've simplified my whole equation by cutting down the number of terms by 1. Now I want to keep on doing that because I want to get rid of this 3 term. I just want my x term on the left. So bring in a new color. The opposite of adding 3 is to subtract 3. The opposite of adding 3 is to subtract 3. Or we could add a negative 3. Makes no difference, right? The point is, I'm introducing this new operation of moving to the left 3 to counteract the original operation of moving to the right 3. And if I started at 3x, if I started at 3x, jump to the right, jump back to the left by the same distance, I'm right back at 3x. Again, you don't have to write that plus 0 term. Just say 3x. I'm starting to the right at 8. I move to the left by 3, so that's 5. Whether I say 8 plus negative 3x or not 3x. Whether I say 8 plus negative 3 or 8 minus 3, I'm still getting 5. Now I have one more operation to go. This is just a single number with no operation. This has an operation of multiplication, and I have a choice. I can either, I'm running out of colors here, I can either say 3 times x times 1/3 equals 5 times 1/3, and say 3/3 is a whole, 5/3 is 5/3, and 1 times x gives me x. Or I could say x times 3 divided by 3 is the same as 5 divided by 3. This strategy of undoing the multiplication with the new operation of division is probably the more common one. And that works so long as I'm dealing with whole numbers. Right? And I get a fraction for my answer, no big deal. So I'll say the solution is 5/3, or I guess that's 1 2/3, or 1.6 repeating, right? 5/3 is just fine. I can't reduce it, so I leave it that way. Right? So that's, in a nutshell, that's our process. I'm introducing new operations once I've simplified in order to be able to simplify even further. Right? Once I get to this blue stage, I can't simplify. So I introduce new things so that I can simplify in such a way as to get the simplest equivalent equation of all. So look at a few more examples of these in the next video.